policy focus on 1.5 alone. It is not that the whole world falls apart at 1.5. As a matter of fact, based on what we know of the Earth's processes on the Earth in the past, when we were this warm, it actually begins to fall apart already at the levels where we are if you're looking at ice. But for each tenth of a degree, really, of temperature that we rise, even above today, we're going to see more melting, more thawing of permafrost, and most importantly, more global impacts. What this is about is not about preserving these regions in and of themselves, although I think for all of us sitting here, that's important to us too. These are beautiful regions. People live in these regions. Many indigenous peoples live in these regions. But their implications, the implications of their loss is global. And that is what we are trying to bring into the negotiations, into the GST, so that it is understood that 1.5, as is said in the preface of the State of the Cryosphere report released last week, it's not just a preferable option to 2 degrees, it should be the only option. And so we're really working for a strong emphasis on that. So first speaking today, we're going to be addressing the Arctic. We have Dr. Heidi Silvestre of the Arctic Monitoring and Assessment Program, which is sort of the scientific arm of the Arctic Council. So Heidi, please take it away.
Thank you. Good morning, everyone. Thank you, Pam. Good morning, everyone. So the Arctic is a region I fell in love with more than 15 years ago. And as you can see, the Arctic is dominated by an ocean, and on top of this ocean, there is sea ice. And to the dismay of my close ones, this is where I spend a few months of the year every year, on the little archipelago of Svalbard that belongs to the Kingdom of Norway. Svalbard looks incredibly different from Dubai. It is pretty much the total opposite. Right now, the Svalbard archipelago is plunged into total darkness, at least until the middle of February. And there could be the occasional northern lights shining across the sky. But my goal today is, in about 15 minutes, to tell you why we should deeply, deeply care about what's happening to the Arctic. And that everything that's happening in the Arctic doesn't stay there and influences the rest of the world. We're also starting to be fully aware, and the latest science shows us, that the Arctic cannot really tolerate anything above a global increase of 1.5 degrees. Beyond 1.5, we start to see irreversible consequences of climate change in the Arctic, and our future really depends on the health of this region. So what we're currently seeing when we look at temperature anomalies divided by latitude bands is, first of all, that when you look at the polar regions, there is a lot of natural variability. But pay attention to what is happening to the Arctic. What we're seeing is unprecedented warming and extremely rapid warming over the Arctic region. But of course, this warming is not homogeneous. What we're seeing is that some parts of the Arctic are warming much, much faster than others. On average, the Arctic is now warming 3 to 4 times the global average. But if you look at Greenland, Greenland is warming about twice the global average. But if you look at Svalbard and the area around Novaya Zemlya, this dark stain here is warming 6 to 7 times faster than the global average. So things are changing extremely rapidly in the Arctic. So let's remember that, a big part of the Arctic Ocean is covered by sea ice. And sea ice is really a key element of our climate system. It really characterizes the Arctic. Sea ice has a superpower. It is a really large surface. In winter, it's equivalent to the surface of the US and Russia combined. But in the summer months, because it's such a large area, a very bright color, it's almost white. Sea ice reflects a lot of the solar radiation we get back into space. Sea ice helps to keep the Arctic and the planet cool. Unfortunately, that sea ice is extremely sensitive to any changes in the ocean temperature and any changes in the atmospheric conditions. What we've seen is that over the past 40 years, we have lost 2/3 of the volume of Arctic sea ice. And let's be very clear, if we do not course correct our emissions right away, by 1.7 degrees of global temperature increase, we will start to see ice-free summers in the Arctic every single year. And this will have dire consequences. First of all, on the Arctic itself, it would be pretty much like putting a radiator against the Arctic Ocean, a radiator against the Greenland ice sheet, and against the permafrost of the region. But let me first focus on the consequences of the decline of Arctic sea ice on mid-latitude regions. What we're starting to see is that if we have less summer sea ice in the Arctic, the weather systems in mid-latitude are directly impacted. It's very interesting to see that the winds, the polar jet stream, and the strength of the polar jet stream really depends on the Arctic being colder than mid-latitude. If this is the case, then the winds are really strong and really isolate the cold conditions in the Arctic. But the issue is that today, the Arctic is one of the fastest warming regions on Earth. So the strength of the polar jet stream is diminishing. And pretty much like a river that is slowing down, the jet stream is starting to meander, to create this wavy pattern. And the wavy pattern can dramatically influence the conditions we have in mid-latitude regions. I mean, look at this. This is a real observations. And you can see that during the summer months, the patterns, the waves of the Arctic can have a dramatic amplitude. This will create really extreme weather conditions in mid-latitudes. For example, we could get persistent abnormal cold conditions in mid-latitude, but we could get also the opposite. We could get extremely hot conditions persisting for weeks and sometimes months, drying certain regions of the world. So the more we lose Arctic sea ice, the more weather extremes we get in mid-latitudes, and some of these weather extremes can even catalyze climate change even more. For example, when you think of really dry conditions that can generate wildfires, these wildfires emit a lot of carbon emissions, but a lot of soot as well, accelerating climate change even more. One of the most terrifying studies I've seen over the past few months link the diminishing Arctic sea ice with the health of our agriculture. Because behind the decline of Arctic summer sea ice is also the health of the bread baskets of the world. And this paper is telling us that until now we've been underestimating, our models have really dramatically underestimated the fact that we could get low yields synchronous in different parts of the world. For example, in North America, in Europe, and in Asia, impacted by the different consequences related to the lack of summer sea ice. Some regions could get way too hot, way too dry. Some other conditions could get much colder. These could actually happen at the very same time. So the bread baskets of the world, or food security, is directly connected to what is happening to the Arctic. But remember, I told you that the more sea ice disappears, the warmer the Arctic will get, and the warmer the Greenland area will get. Well, let's look at that. Let's look at the Greenland ice sheet. We know that the Greenland ice sheet hasn't been waiting for sea ice to disappear to start losing huge amounts of ice. So this is a little video that shows you the regions of the Greenland ice sheet that are melting faster than others. Our future is directly connected to the future of the Greenland ice sheet because it holds enough ice, enough land ice, to increase sea levels globally by up to 7 meters. And Greenland is currently the Earth's largest regional contributor to sea level rise. It is actually producing a much larger sea level rise than Antarctica. And Antarctica is, of course, much, much bigger. What is important to remember is that for every centimeter of sea level rise, this will flood an extra 3 million people. This is already costing billions of dollars of damage for every single storm. And if we keep going on the current path of emission, we will be talking about meters, not just centimeters of sea level rise. So what does that look like if we stay on the current trend of emissions? Let's look at different parts of the world. We know that 1 meter of sea level rise is now already locked in for the future, no matter what we do. But this is really up to us to decide how far we want to take this. So today, our current emissions pathway means that waters could jump by 1 meter in the next 50 years. And places like Bangladesh, that you can see here on the map, would have terrible consequences, such as massive migrations and also important changes to agriculture because of salt water intrusions. Let's continue with Pakistan. We could get 3 meters of sea level rise in the early 2100s under current emissions, which would cause unthinkable damage in places like Karachi in Pakistan. And if we look at places like the Bahamas, low-lying nations, they would practically be gone with 3 meters of sea level rise. So let's be very clear. When we look at these ice sheets, we know that only very low emissions, only 1.5 degree limit, would reliably maintain our ice sheets, preventing massive long-term sea level rise. Not only Greenland is losing huge amounts of ice, but also very quickly, the polar glaciers that we have in the Arctic, this is their contribution to sea level rise since the 1970s. Very simple. When the curves go up, it means that the glaciers are losing more and more ice, contributing more and more to sea level rise. We don't just have ice sheets, sea ice, and glaciers in the Arctic, we also have a huge amount of permafrost. Permafrost is the frozen ground. It covers 22% of the land mass of the Northern Hemisphere, and it holds vast amounts of ancient organic carbon. The more permafrost thaws, the more CO2 and methane are being released in the atmosphere. And what's very important to remember is that those emissions will not slow down for at least 200 years, making this an issue of intergenerational justice. So today, annual permafrost emissions are about the same as the country of Japan, which is the 7th largest emitter in the world. But things could get worse. Actually, if we reach 1.5 degree globally, emissions from permafrost through 2100 will be about as large as the emissions from the country of India today. If we reach 2 degrees, those emissions will be about as large as the EU's every single year. And beyond 3 degrees, they will be about as large as the emissions from the USA or China through 2100. But remember that we have a lot of people who live on permafrost today. Just in the Arctic, we have 7 million inhabitants. And so the thawing permafrost is causing the loss of Arctic land, but also really important damages to infrastructures because the ground is sinking evenly underneath these infrastructures. And the AMAP report states that 66% of Arctic infrastructures are built on permafrost. So the only means available to minimize these risks related to permafrost is really to hold global temperatures increases to 1.5 degrees. Let's move on to our polar oceans. They are great at absorbing carbon. But unfortunately, the more carbon they absorb, the more acidic their water gets. And today we're seeing in the polar oceans the highest rates of acidification on Earth. And this impacts the entire marine food chain. If you look at the picture on the right-hand side, the little theropod you see here, they're very sensitive to these expanding corrosive waters in the Arctic. Theropods are hugely important. They serve as a source of food for young salmon, Arctic cod, char, and other economically important species. And of course, all the oceans are connected together, and what we're seeing that the polar waters are not only getting more acidic, but they're also getting warmer. In the Arctic, we're starting to detect extreme marine heat events. They're becoming more common, and the temperatures go far beyond the levels that polar species evolved for thousands of years to survive in. What we're also seeing is that the waters around the Arctic and Antarctica are the engine of the entire global circulation system. The problem is, because the polar regions are getting warmer and because of the ice sheet are releasing huge amounts of fresh water into the oceans, where we're starting to see a slowdown of the global circulation impacting every single region on Earth. So I'm approaching the conclusion of my presentation. If we look at the tipping points of our climate systems, we're starting to see that actually the Arctic contains 8 out of these different tipping points highlighted here in yellow. So the Arctic truly, truly matters for our entire climate system. And if you look at the temperature that corresponds to these different tipping points, well, they start just beyond 1.5 degrees. So this is the strongest argument not to cross these tipping points that will affect each and every single one of us and everything we have built and everything we have ever loved on this planet. Let's not make the wrong decisions. We know that the best way, the most efficient, the cheapest way, and the safest way to avoid crossing these tipping points is to phase out all fossil fuels. But what we've seen during this COP28, is that some other pseudo-solutions are also being developed. And I have a quick slide just to mention to be extremely careful when it comes to geoengineering. Let's have a very serious assessment of the perhaps positive but also negative consequences on geoengineering. So to conclude, today we are at a very important time of the COP process. We know that the first global stocktake must include these physical realities, must include the physical limits that are placed on Earth by the reaction of the Earth's ice for each increment of warming above even today's temperature, let alone 1.5 degrees. Again, we know that only urgent fossil fuel reductions, only urgent reductions of fossil fuel emissions can prevent crossing these tipping points. And this is important. We cannot negotiate with the cryosphere. We cannot negotiate with the melting points of ice. I'll stop right there. Thank you very much.
Thank you so much. So this is a good lead-in in many ways because Heidi covered actually some things that are going on in the other pole, in particular sea level rise, because Greenland holds only 7 meters of sea level rise. As you're going to hear now, Antarctica holds quite a bit more. So our next speaker is Dr. Florence Colleone. She is the co-lead for SCAR's Instant project. And she will be speaking primarily about committed sea level rise from Antarctica.
So thank you, Pam. So effectively, many important things are happening in all the cryosphere now, and actually I wanted to take you to the South Pole and to speak about Antarctica, but from a slightly different point of view, because most of the urgencies we are speaking about are happening now. But I also would like to take you in a time travel somehow, because this also matters not only for our few decades of human life, but also on different generations in the future. So about the tipping points, I think it's really important to stress out that all the ice sheets actually have a huge uncertainties on whether they have crossed their tipping points or not. We all know that Greenland effectively is melting every summer, because I think everyone taking a flight and flying over Greenland can see during summer the melting ponds and lakes from meltwater forming during that season. So there is no doubt that there is something going on there. But Antarctica, it's a bit more tricky because it has different parts. I mean, a part that is more sensitive to regional and global warming, and part that is apparently less sensitive to it. But for sure, no melting pond or very little one forms at the surface, so it's not very visible what's going on, but something's going on there. And assessing the tipping point is really important because, well, I mean, this is what determines if we need to phase out fossil fuels or not. If I understand, here people think that we should not do that. It's not necessary because we don't know anything about science, right? So, so what about projecting global mean sea level? What do we know? So if we take all the observations we have and the science we know about projecting sea level, this is what we came out if we increase global mean temperature by 1.5 degrees, 2 degrees, or 3 degrees, okay? So you can see that by the end of 21st century, all contributors to sea level rise, so ice sheets, Greenland, Antarctica, glaciers, and also the thermal expansion of the ocean absorbing the heat that we are producing in the system, they could lead to a little bit less than 1 meter in the upper bound of uncertainty of those projections, okay? So between the 1.5 scenarios and the +3 scenario, which represents our current rates of emissions, actually, it's not double, of course, but it's much more. But we know that already with 20 centimeters that we have been producing over the 20th century, we are increasing the impact of our all extreme weather events on the coastal areas. So imagine with 3 times more or 4 times more, how large would be the damage on the coast. But the real impacts, actually, we are not seeing them now, and we will not see them on the 21st century. Even if they are already scary, this will be on the long term, and this is because the physics of the ice tells us that. And if we look at the projections until 2300, for example, we can definitely see the divergence between all the sea level scenarios, okay? And there is a lot of uncertainties on those projections. You can see that the bar are very long, actually. But this is because we are still uncertain on the behavior of Antarctica. Greenland is melting, it's a terrestrial ice sheet, and so it will continue to melt with an exponential acceleration rate, unfortunately. But for Antarctica, it's a bit more tricky. So Antarctica, if you remove the ice and you look at how is the bed on which the ice is lying nowadays, you can see that all the brownish area are the bed that is above sea level, but all the light blue areas corresponds to the areas that are below sea level, which means that the Antarctic foods in all those areas are vulnerable to oceanic warming because they have the foods underwater. And as such, it makes the ice sheets particularly vulnerable to both atmospheric warming, as Greenland, but also to oceanic warming in larger extent than Greenland. What does that cause? We are actually investigating in the ice sheet community what we call instabilities in the ice sheet dynamics, because you know an ice sheet is not a static body, it's flowing, it's living, and so when it reaches the coast, it calves, it makes icebergs, and sometimes you see in the newspaper huge icebergs that are drifting away in the South Pole, but also in the North Atlantic. So in Antarctica, the areas that are below sea level, actually, they thin under the action of oceanic warming, and when it's too thin, those floating parts actually disintegrate into icebergs, and it destabilizes the ice sheets because, you know, they act as tap from inland flow. If you remove the tap, you accelerate the flow up to the ocean, okay? So if you disintegrate this platform, you cause a large discharge, a very large and quick discharge of ice into the ocean. That's what we call in our community the marine ice sheet instability. Then there is another one, actually, that is still under investigation. Is caused by the melting at the surface of this floating part of the Antarctica, because you know you all know that when the floating, the freshwater, come to crevasses that forms at the surface of a glacier, when they freeze again during the winter, the volume increases. Okay, this is physics. So it creates some fractures into the ice shelf, into the floating parts, and so it accelerates the disintegration of those parts, which are already thinning by oceanic warming. Okay, so we have these two kinds of instabilities that we are investigating in the community. And so they both create a large discharge of ice into the ocean. And I say we are investigating them because they take a couple of centuries to really disintegrate those platforms. So it's definitely beyond our time span of observation. Okay, we have only a few decades of observations, and we can definitely not guess in the future how it will be. So we know what the models show when we try to input some physics is that it takes a couple of centuries, but it has a fast trigger, a tipping point, a threshold in oceanic temperature that if crossed, those platforms disintegrate. And it has long-term consequences, creating multimeter sea level rise. So if we look at what has been done, for example, in one of the West Antarctic area that is most sensitive nowadays to oceanic warming, you can see that in the simulation, it starts in 2015 and finishes in 2300, and you can see that it all disintegrated. Okay, this is a model simulation. And now if we integrate into those projections that do not account for such, let's say, striking instabilities in the model so far, we can increase very much the projected long-term sea level rise above 2 meters until the current NDCs, because those projections, unfortunately, are missing the glaciers' contributions here and the ocean thermal expansion. So that's why I wrote larger than 2 meters, because it's probably reaching 3 or 4 meters, actually. Do we have evidence of such instabilities? Because then you will say, okay, it's all physics, it's all science fiction, we are inventing physics. We are very good at that as scientists. We can invent many science just to make fun, or, you know. But we do actually have evidence of such instabilities in the geological records. And if we look at the geological records, they tell us that an ice sheet can really retreat when it destabilizes in a few centuries. So what the physics we have in the model, perhaps it's still coarse and needs more investigation, but has the right timescales of those processes. And we have been finding them in many different sectors of Antarctica, actually, those sectors that are vulnerable to oceanic warming nowadays. So what does the evidence say about what happened in the past, many million years ago and up to now? So, well, if we look at sea level reconstruction in the past, so 23 million years ago, it was a period where the global temperature was about plus 5 to 9 degrees above present-day sea level, with a very large CO2 concentration. And you can see that sea level range about 20 to 30 meters, with some kind of uncertainty in the reconstruction. Then we go back in time 3 million years ago, which is a period with temperature warmer by 2 to 4 degrees compared to today, with a CO2 around 400 ppm and sometimes peaking to 500 ppm. And we can see that our ice sheets were melting and producing sea level rise in the range of, let's say, 15 meters in average, with some kind of uncertainty in between 10 and 20 meters. It is being refined, actually. And then we jump in one of our closest interglacial 1 million years ago, and with temperature warmer, global temperature warmer by 0.5 degrees to 1.5 degrees, let's say, roughly, with a CO2 level of 300 to 400 ppm. So we are already lower than the current rate of CO2 we have in the atmosphere nowadays. But still, ice sheets were disintegrating and melting, producing sea level rise from 15 to 20 meters. Then now we jump in the closest interglacial, where we know for sure that the ice sheet contributed large amount of sea level rise disintegrated, because we definitely see the extent of the ice sheets. And temperature was warmer by 0.5 degrees to not more than 1.5 degrees for sure, with a CO2 concentration lower than 300 ppm. And we have a sea level rise above 5 meters. Okay, so this period produced something that is equivalent to what we have under our current rate of emission, NDCs plus 3 degrees in average. Those were below 1.5 degrees warming compared to pre-industrial, and we still have high multimeter sea level rise produced at that moment. So 1.5 degrees already triggered multimeter sea level rise. That's why we are pushing this boundary to be respected, actually, because we know that 2 degrees is definitely well above this 5-6 meter sea level rise. So if I put our projections back here to compare with paleo, you can see that we are completely in the range of what the geological and glaciological evidence says. So we are not inventing anything here. We're not playing with science. And what we see is that it happened even with this very low temperature warming target. So that's why it's really important that we respect that. Every tenth of degrees matters, truly. And if we stop our emission, we already anyway have committed to 30 to 60 centimeters of sea level rise. So it means that in any case, because of the thermal inertia of the ice, even if we stop tomorrow emitting anything, we will anyway have a sea level rise by the end of the 21st century of this amount, and much more in centuries to come. At 1.5 degrees, we can still anyway preserve large part of Antarctica, because 5 meters is the contribution of all parts of the system: ocean, glaciers, Greenland, and Antarctica. Above 1.5 degree, we create irreversible multimeter sea level rise, and that's past archives telling us that. So we cannot avoid anyway multi-generational adaptation. However, we still need to strongly push for this target of 1.5 degrees. Thanks.
I guess thank you for that terrifying presentation, journey into the past as well as into the future. Moving now to the third pole, and in that I'm including especially really all mountain regions, but with a focus on the Hindu Kush Himalaya, is Dr. Regina Hawk, who was the IPCC AR6 coordinating lead author for the Mountains chapter.
Okay, thank you. We heard a lot about Antarctica and Greenland now. I will bring you now to the world of glaciers outside the Greenland and Antarctic ice sheet, because they matter for sea level rise and have the decline has major impacts on human and natural systems. There are 250,000 glaciers in the world. They cover an area of about 750,000 square kilometers, which is about the size of Texas or the size of the UK and Spain together, or 4.5 times Nepal. If these glaciers melted, sea level would rise about 40 centimeters. I focus here in this presentation on the glaciers in high mountain Asia, but also give a global overview. Glaciers around the world lose mass and retreat worldwide. Here an example from Argentina, an example here from Iceland, where just in a few years the glaciers have massively retreated. So just in 13 years, a major retreat of this glacier. Another example here from the Imia Glacier in Nepal, massive changes in just a few years. And now many smaller glaciers are disappearing around the world. Here an example from Switzerland. And some regions have experienced enormous heat waves and enormous losses within just a very, very few years. Here, Switzerland has lost 10% of the total glacier volume just in 2022 and 2023. Globally, the glacier mass loss is increasing. What you see here is an increased thinning rate of now 50 to 60 centimeters of thinning if you average over all glaciers in the world outside the ice sheets. So 0.5 meter of thinning every single year. But how will the glaciers change in the future? What you see here is projections of all glaciers in the world globally and differentiated for 19 regions in the world. And what you see is one of the means 100% of the ice is there, it's relative to 2015, and 0 is nothing is there anymore. You see in all regions, massive declines, mass losses are projected. Larger mass losses are projected for the higher emission scenario than the lower emission scenario. And worldwide, we project here a mass loss of about 20 to 40%, depending on the emission scenario, and a cumulative sea level equivalent by the end of the century of about 8 to 17 centimeters, just coming from the small glaciers around the world that are not the ice sheets in Antarctica and Greenland. What we see is in regions where there's little ice at the moment, we project almost complete deglaciation with a higher emission scenario. Only in the high Arctic, in the polar regions, the mass losses, the relative mass losses are less, maybe 10, 20, or 30%. And the high mountain Asia regions are somewhere in the middle, but also massive mass losses projected by the end of the century. What you see here is a projection of how much mass is remaining by the end of the century in each of these pixels here that have glaciers in the world. Blue is 100% is remaining, dark blue. Dark red is almost nothing, and all the black circles means nothing is remaining. And what you see, even at 1.5 degrees, there's many black circles, meaning that all glaciers will be gone by the end of the century for even a 1.5 emission scenario. And here, in some regions, even with 1.5 degrees, in most of the regions of these regions here, circled here in green, the glaciers will be gone. In high mountain Asia, still a lot of ice left with 1.5 degrees, but also in some regions, the glaciers are gone. Here for 2 degrees, you see more red and more black circles. 3 degrees, 4 degrees. So with 4 degrees, many regions in the world will have no glaciers at all, and only in the very high Arctic here in Canada, northern Greenland, there's still quite some ice left. We also simulate that by the end of the century, with a 1.5 degree scenario, half of the glaciers in the world, more than 100,000 glaciers will be gone. And that's with 1.5 degrees. You see here for different size classes, what we see is, of course, most of the glaciers that will be gone are very small. They're less than 1 square kilometers. We also see a linear relationship between the global temperature increase and the mass losses worldwide. So the warmer it is, the more mass is lost and the more area is lost. And as you can see here, for instance, 3 degrees, we have a mass loss of about almost 50% of all mass on Earth. So that means every degree makes a difference. So limiting the global warming reduces the mass loss and is really crucial. Here you see the same type of graph. We have the global temperature increase on the x-axis versus how much mass is remaining for all 19 glacier regions in the world. And we see this linear relationship everywhere, but the strength varies. But there's a nonlinear relationship here in regions where there's very, very little ice. So it doesn't matter anymore if it's 3 degrees or 4 degrees because the glaciers are gone in these regions. High mountain Asia is here somewhere in between, also a large dependency of how much ice remains by the end of the century, depending on the global temperature increase. It makes a huge difference here if it's 1.5 degrees or like 3 degrees. What you see here is simulations beyond 2100. And that's where the differences become even larger, especially in high mountain Asia. What you can see here, for all scenarios, 1.5 degrees or 3 degrees, there's massive mass losses until the end of the century. But for 1.5 degree, you see many glaciers actually are growing again, and the glacier mass in high mountain Asia here is increasing. So it makes a huge difference between 1.5 degrees and 3 degrees, especially here beyond 2100. The glacier decline has major impacts on livelihoods around the world, and it's often featured also much in the media in recent years because it can have dramatic impacts. One impact is that glacier retreat affects stream flow. First, with the glacier decline, when the glaciers start melting more, runoff goes up. But then, at some point, a point is reached where the glaciers are so small that they cannot sustain anymore this input to the rivers, that the runoff goes down. And this increase can be up to 50 or 60%, depending where you are. Here's some simulations about this peak water, when it happens, because this is important for water resources. When do we have peak water? When does the water from the glacier start going down? And what you see here is in colors the year when it happens. Blue happens late in the century. Red, dark red has already happened, so the runoff from the glaciers goes down. You see, for the higher emission scenarios, there's more variability. And you also see there's large spatial differences, like the monsoon-fed rivers, like the Ganges or Brahmaputra, they hit peak water before 2050, whereas the westerlies-fed rivers, they hit peak water later. But it's not only total runoff that's affected, but also the seasonality, when the water is coming, and that matters for agriculture. And what you see here is how much will the runoff increase or decrease in June, July, August, September, October in high mountain Asia, in the Asian watersheds. And blue, so the key message is here, blue is more water, red is less water. And you see substantial differences between the seasons here, between the months, more water in June, but significantly less water in August. And I want to emphasize here, these simulations are for drainage basins that are more than 5,000 square kilometers. And the glacier part is only like 2, 3, 4, 5%. There's hardly any glaciers in these catchments. Many people in these catchments probably have never seen a glacier in their life, but they are affected by these declining glaciers, by the declining glacier mass. So even in basins where there's hardly any glaciers, the glaciers have a major impact on the runoff in certain months of the year. The glacial decline also affects glacier outburst floods. We have seen that the number of these lakes that are adjacent to the glaciers has increased and will increase. And that increases the risk for glacier outburst floods. Glacier outburst floods are the most devastating glacier hazards one can think of. In 2013, more than 4,000 people died when here this lake at the side of the glacier drained catastrophically. The glacier decline also has an impact on cultural values. For instance, there is UNESCO World Heritage Sites, and in a number of these sites, the glaciers were among the principal or secondary reason for the World Heritage inscription. But almost half of these World Heritage sites could lose their glaciers by 2100. So I just want to conclude here. Every increase in temperature matters. And limiting warming to 1.5 degrees is really crucial to minimize the negative effects on sea level, stream flow, glacier-related hazards, water quality, and landscape changes. Thank you.
Thank you so much, Regina. So our final address will come from Dr. Bill Hare, the founder and CEO of Climate Analytics. He will be addressing both the whether or not this science, I suppose, is breaking through, or whether 1.5 is breaking through, but also the possibility to do so, which I think is a really important message. One of the things that I know that we're fighting organizationally is references to, oh, we've already passed 1.5, we can't prevent it. Nothing could be further from the truth. It's still a decision on our parts. So, Dr. Hare, please.
Thank you, Pam. So if I've got the right PowerPoint here. Just working? Good. Thank you. And thanks for those really brilliant presentations. I've really rarely seen such good, clear, solid update on the science knowledge. It's quite shocking. I've been working in the field for a long time, and it's really a bit difficult to see all that come together in one space, one place. Very important messages for the COP here. I wanted to just step through, and I've been asked to step through where we stand on climate action. It's one of the things I do now is work with the Climate Action Tracker, looking at what's going on nationally, globally, and so on. But I wanted to start out a bit with the 1.5 degree issue. where we stand. Get this working. Yeah, so the IPCC has been looking at the question of what are the big risks that we face ever since 2001. Third assessment report. We came up with this burning embers diagram, and it's regularly updated. Methodologies change, but one of the main messages that I think you're seeing here from the cryosphere stories from the science, and that the IPCC is pulling together across the 5 risk categories that we have put together since 2001, is that every time we look at the science afresh in the IPCC assessments or in other contexts, then we see major risks at lower and lower levels of warming. And I think that's very true of some of the updates we've had here on Greenland or Antarctica, where it's been very controversial for decades as to whether or not anything really significant would happen, and you can go back to IPCC assessments and find often quite ambiguous or no findings at all. But it's becoming very clear that the 1.5 degree level of warming here, which is the lowest one you see, is the one where across a whole bunch of risk categories, not just cryosphere, you stay out of the moderate, high or very high risk zone, and it's often the only way. So where do we stand in understanding what emission reductions mean? And I've drawn out a few images here from the literature on what it means to delay emissions, what it means to overshoot 1.5 degrees, give you a few examples. Here's a paper from a few years ago looking at the critical window of action and the implications of every 5 years delay in peaking and dropping emissions at the rate needed to limit warming to 1.5 degrees. And what this work shows is that essentially every 5 years delay in peaking emissions adds longer term 20 centimetres of sea level rise. In other words, the cost of delay in sea level rise terms, in other words, impact on the cryosphere, is something that will be felt over centuries. It's not something you see immediately, but it's a long-term message, and that came through, I think, very clearly in the presentations that we heard. So there's a very big risk to a delay in peaking emissions, and that's one of the things that's on the table in the global stocktake, is to get parties to resolve to peak emissions. We look at the question of overshooting 1.5 degrees. This is a paper by Carl in review now, Carl Friedrich Schleusner, looking at the implications of overshooting the 1.5 degree limit in the Paris Agreement. And essentially 100 years of overshoot is calculated to result in 40 centimetres of additional long-term sea level rise you wouldn't have likely had you avoided that peaking. So overshooting 1.5 degrees has consequences, and they're not good. Looking a bit at the Asian water towers story, which affects and will adversely affect billions of people in coming decades, overshoot also has a significant risk here. This is a recent paper which shows the projected loss of ice, if you like, in the Asian water towers at different levels of warming. And the bottom line message here is that 1.5 degrees will actually keep a lot of ice in this region. Overshooting significantly 1.5 degrees will cause a greater loss and take many centuries to recover from, affecting the water supply for billions. So there's a risk to overshoot here as well. Now, obviously the question comes up, what about the Paris Agreement's 1.5 degree limit? Now, I had the privilege to be involved with, very directly involved with negotiating Article 2.1 and 4.1 of the Paris Agreement. And it's not about a 2 degree limit. The Paris Agreement long-term temperature goal refers to holding warming well below 2 degrees. Not 2 degrees, not below, but well below. And that, from the science point of view, means warming needs to be lower than 1.6 to 1.7 degrees. And that's what you find in the IPCC assessments, starting out with a 1.5 degree report in 2018 through the AR6, that 1.5 degree pathways are defined as those that have no or limited overshoot. The limited overshoot is about 0.1 degrees. So absolutely correct that the Cryospheric Initiative is pointing out the risks at 2 degrees, but the Paris Agreement limit is actually very, very close to 1.5 degrees, whichever way you look at it. Now, is it still feasible given the way emissions are going? Well, the Working Group 3 report of IPCC, the mitigation report, has shown that it is. It shows that strong action can still get us into the pathway needed to limit warming to 1.5 degrees. It basically means we need to be reducing emissions by 43% against 29 levels by 2030. It means we need to be getting out of fossil fuels fairly quickly, and we need to be getting towards net zero CO2 emissions by 2050 to have any chance. Now, from the physics point of view, if we get into that pathway, there is a modest 50% chance of holding warming to 1.5 degrees, or only slightly above that. The question now is essentially political and economic. Can our political system here agree the measures needed to do it? Now, and this year we've seen really extreme temperatures, by some estimates, some days above 2 degrees above pre-industrial in November. I know there's a bit of controversy amongst those that do temperature time series about this, but let's say it's a very, very clear warning. But it doesn't mean the Paris Agreement's limit is busted. The Paris Agreement 1.5 degree limit is a climatological average increase due to human-induced activities over 20 years. So what it means if we're seeing months and even a year at 1.5 degrees or above is it's a very clear warning sign that we are simply running out of time. So it doesn't mean it's busted, but it needs to be a real kick in the pants to politicians to actually get on with doing things. I know there's a 1.5 degree lost story out there. You read The Economist or other places, but the point there is the one that Fatty Birol made, that giving up on it will only advantage the fossil fuel industry. You can call them the carbon boosters, but that's the only benefit of saying that 1.5 degrees is lost, is to help those that really benefit from that. So looking at where we stand now on the Paris Agreement commitments, for better or for worse, the Paris Agreement agreed that the commitments made by parties were nationally determined contributions, NDCs. They're not dictated by any body, agency, international organisation. They're up to countries to come forward, put forward actions, targets for 2030 that align with their perception about 1.5 degrees. So we're seeing a lot of countries having updated their NDCs, but we're a long way from 1.5 degrees. Now, the Climate Action Tracker, set up in 2009, is in the business of adding up all of these country emissions and using methodologies to project forward over the 21st century to try and estimate what the total warming effect of those policies, targets that we see in place in the short run, mean for the long run. So the latest update now is that we have projection of around 2.7 degrees of warming for current policies and actions. For targets, it's a bit better, close to 2.4 degrees or so. But the problem here is that we're not seeing much progress. So if you look at another picture, which is the emissions gap, which is the gap between where emissions need to be in 2030, and we'll be doing 2035 from next year, and the green pathway, the 1.5 degree range of emissions from IPCC scenarios, you see it's quite a big gap, many gigatons. And we're a long way from closing that gap. Ever since we started looking at this in Paris, we saw a progressive improvement in the global warming outlook. There were some setbacks. You can look here. The blue line is the policies that countries have in place. The grey line is the targets, pledges. You can see the Trump election set things back, withdrew from the Paris Agreement. But overall, the trend was improving. But this is the first time that CAT has basically come up with the assessment that things have not improved in the last 2 years. We do not see a significant improvement. There's a bit of noise in the data, so others might come up with slightly different approaches, but the bottom line is no one I know has come up with a picture of any real significant improvement despite the pressure to actually move forward. Now at this COP, there's been a number of initiatives announced by the presidency. I'm not going to go through them all, but the Climate Action Tracker has had a crack at trying to evaluate, in emission number terms, what the initiatives mean. There's some 32 initiatives, 42 new pledges. Now, we found that there's a lot of overlap with the commitments made in Glasgow, that the governments already need to take a lot of the action that's been announced in order just to meet the NDCs, which they're a long way from actually achieving. A lot of the announcements are very difficult to measure, track, trace, monitor, verify, very, very hard. So there needs to be a lot of follow-up on this. The oil and gas accelerator initiatives we looked at, very much pushed by the presidency, but essentially it doesn't add up to a lot. It looks to us like a prime example of greenwashing, well, big announcements, a lot of talk, but actually not much going on. If we try and put this in the overall picture of the emission gap, estimating the overall impact of COP28 initiatives, we find a lot of overlap between the NDCs and what governments should be doing. We find a small fraction is achievable and a large amount is probably not going to happen. So that's the picture we've got. Now, turning to what's on the table now in the global stocktake, I think everyone here is aware that there's a big push on to get a fossil fuel phase-out agreement or language to that direction in the global stocktake. From the point of view of the emission pathways we look at for 1.5 degrees, I think everyone knows that fossil fuel production needs to fall quickly, roughly 40% by 2030 and ongoing beyond that. We know from the UNEP fossil fuel production gap report, which we've been involved with others, that commitments to expand fossil fuel production are really quite extraordinary. They haven't decreased in the last years. The red line is the production that we see coming out of country projections. The lowest lines are the 1.5 degree pathway emissions, and you see the gap is growing. It's not getting any better. So that shows what's at stake here. We've all read that there are an extraordinary number of fossil fuel lobbyists here. Certainly in the history of my involvement with this process from the very beginning, they've always been present, but they're here in extraordinary numbers. So we're seeing fossil CO2 emissions at peak levels. We're also seeing fossil fuel lobbyists at peak levels. Now, we need to know that fossil fuel emissions need to fall rapidly. I think everyone understands that. The International Energy Agency Net Zero report has reinforced that. We know that on the optimistic side that fossil fuel demand could peak even this year due to the rapid growth in renewable energy rollout. The rate of rollout of renewable energy generation is far greater than the growth in electricity demand, and there's a crossover happening where that will start to displace fossil fuel generation, and the rise of electric vehicles, to take two main examples, mean that we could see, if these patterns continue, a peaking of total fossil fuel demand and at least fossil fuel demand in the power sector. Now, the other issue going on here, coming to the second last slide, Pam, is the question about the fossil fuel language being debated in the global stocktake, where there's a big fight going on over the term unabated. The reference in the text now is towards an unabated fossil fuel phase out. That means you phase out fossil fuel emissions that you haven't reduced emissions from. There's a big catch that unabated looks like a loophole. You could even go, say, stronger, as a Trojan horse to allow ongoing expansion of particularly gas and oil production. That carbon capture and storage projects to date haven't really done very well, to put it mildly. They've a long history of underperformance. So there's a lot of concern. I know it's not universally shared, but by many in the mitigation community, that allowing CCS in a COP decision here will risk discovering in 5 years' time that actually nothing much changed. So that's a big problem. So one of the issues here, on my last slide, relates very directly to the global stocktake fight going on now in the corridors and meeting rooms, is about what kind of fossil fuel phase out is agreed here. And the science is very clear that we need to do that. And the pathways all show, as I said, 40% reduction in fossil fuel production by 2030 and ongoing steep declines through the rest of the decades to 2050. So that's where I wanted to leave it, Pam. Thanks.
Thank you. And we're actually running ahead of time, Bill. That was mostly to check, I know there might be some parties that potentially would want to speak here. So I just wanted to double check. I don't see any of the invited guests, but if you are there, please raise your hand, and we're happy to have you come up. And otherwise, we will open it up to question and answer at this point. I'd like to lead with that for Bill in terms of the Earth system. I mean, I think from a cryosphere point of view, what we've been focused on indeed is phase out of fossil fuels, because we need to hold temperatures close to 1.5 as possible. And then it is CDR, or negative emissions, that will then begin to bring temperatures slowly down. I would say that in the cryosphere science community, I think some of the estimates that we saw in terms of delay and time to overshoot, lots of active research in there, but I've certainly heard from, say, Greenland ice scientists that a few decades at 1.6 would be enough to, trigger the Greenland ice sheet, and there's a fair amount of debate in the West Antarctic ice sheet community whether West Antarctica actually tipped slightly below 1 degree. I think that's correct, Flo. Yeah. So then, if the Earth system maybe requires negative emissions just to stabilize, I'm wondering if you could clarify that point, because that means it's even more urgent.
Okay. Well, look. I guess from the physics point of view, right, we know that if we can get CO2 emissions to zero, that there's a reasonable chance that warming will stop, right? So we know that. That's the first task. And there's good grounds to believe that if you can pull off negative emissions, that, and you can do that at scale, then you will draw down CO2 concentrations even faster, and hence warming. And there's a bit of debate in the literature. There's a nice paper by Kirsten Ziegfeld recently, I think in Nature Climate Change, just pointing out that we can't really fully rely on that because of the physics of the way the Earth system works. It might not work out the way that we would like. But yes, ultimately we're going to need negative CO2 emissions at scale in order to have emissions, order to have temperatures drop. Now, the 1.5 degree pathways, if you look at the low and no overshoot pathways, and particularly those in category C1A of the IPCC assessments, they also comply with Article 4.1 of the Paris Agreement, which is to bring emissions, global greenhouse gas emissions, to zero in the second half of the century. These pathways get back towards something like 1.2 to 1.3 degrees by 2100. They don't all rely on massive negative emissions. But those that don't get out of fossil fuel emissions a lot faster. So the more you allow fossil fuels in the system, the more CDR, of one form or another, technological or nature-based, that you will need to get. On the nature-based side, one needs to be very aware that nature is not doing very well, and that once you start to stabilize CO2 concentrations and have them going down, you will start to lose the benefit of CO2 fertilization for the terrestrial biosphere, and you will start to have ongoing issues with the Southern Ocean carbon sink as well, as we know. Antarctic scientists have a lot to say about that. So one needs to be very careful about relying on that. The first and foremost is to get fossil CO2 emissions to zero and carefully roll out negative emissions technologies in order to get that temperature dropping. And that, I think, for the cryosphere is absolutely critical. But also I'd point out that if you're thinking about deadly heat, and there's enormous lot of work done on that in recent years, and you look at the deadly heat maps for 1.5 degrees, you could really begin to wonder what a 1.5 degree world would look like. We didn't know that when we negotiated the Paris Agreement's 1.5 degree limit. We did not know that the deadly heat impacts could be so grave at such a low level of warming. But there you've got hundreds and hundreds of millions of people that could, within a very few decades, be affected by non-compensable heat and humidity, particularly in South Asia, North Africa, and other places.
Thank you. I don't know if there are any comments to that. We don't have any permafrost scientists here, but I will say that, of course, when human emissions are down to zero, we need to count on permafrost emissions, as shown by Heidi, on a scale of a major emitter for a couple of centuries, actually. And that'll be higher for however temperature rises. So we have Maya running the mic. Yeah, and then you next. Yeah.
Thanks, Pam. What a wonderful panel. Thank you so much. Well, my question is really around, with this deadly heat, whether the demand for energy has been factored in, because that obviously is going to accelerate hugely. And I just wondered if that's been much of the discussion. And I feel that this sort of presentation should be much more visible because I haven't heard much of that being factored into the, we're talking about emissions reductions and we're talking about alternatives, but the alternatives are struggling anyway. So are we going to have enough alternatives to also accommodate for the increase in heat?
Any takers on that?
Well, look, the 1.5 degree pathways, if I can put it, compared to current policy pathways, do provide everyone on the planet with accessible, cheap energy, right? You can find this in the IPCC assessment. So I'm pretty confident that we could scale renewable energy and energy efficiency with the right policies that would provide the populations affected by the heat risks I'm just talking about with energy. And we need to recall that in the last few years, when there's been really extreme heat in India, Pakistan and so on, that the thermal power system has failed. And we know that thermal power systems, nuclear, fossil fuels, are subject to really severe constraints when it's very hot in a way that renewables are not. So I think that it's a much safer outcome and much more economically beneficial. There's a lot of depressing talk around these corridors about how things are not working, but look at the renewable rollout in China. Absolutely staggering this year, and in other places as well. It shows the real potential, and then electric vehicle rollout is starting to cause problems for oil demand, right? It's at scale, it's growing, and I think that should give some grounds for optimism to make sure this becomes a universal rollout at scale. A lot of things need to change, of course, so it's not determined that can go at scale, but it's a very good sign.
Please.
Thank you very much. I'm Cecile Jebet. I'm a Cameroonian. I'm the Wangari Maathai Champion of the Forest 2022 and the UN Champion of the Earth 2022. I just come from Antarctica. I arrived in the 2nd of December. I have a colleague here. We have been there for 21 days in a program on leadership and climate change organized by Homeward Bound. We were 232 women in the 2 ships. So I wanted to confirm that what you have shared, it's very true, and the situation is even going worse. And we need action. And because I was there as an activist, I have a statement here of 3 minutes. If you don't mind, I can read it, and all the audience will understand where we are, and maybe you can help us forward this message to these leaders to tell them that we are all in danger. And if we don't act and concretely, not only discuss and talk, but on the ground, the situation will be worse for everybody. If you don't mind, I have the statement. Thank you. Excellencies, distinguished delegate, dear colleagues, ladies and gentlemen, I'm standing here, but my voice echoes millions of African women walking by my side, mobilizing to heal our lands, our forests and sea. I also represent 800 women with a STEAM background. STEAM means science, technology, engineering, math, and medicines, who are part of the global Homeward Bound initiative. We speak with one voice. Hear us now. From forest and sand to ice desert, I have just been in Antarctica, and I had 3 of the most beautiful weeks of my life. But what I saw and heard broke my heart. World leaders, listen. We are all in a grave danger. This has been a year of ice loss, climate disasters, and suffering. Changes in Antarctica and in the Southern Ocean affect the global climate and therefore impact all other ecosystems and people around the world. Glaciers and polar ice melting causes the sea level and the global temperature to rise. Many of the world coastal cities have much to lose from rising sea levels. For example, here in Dubai, it is projected that 31% of inhabited land will be lost to the sea by 2100, and it was just shown shortly. We all need to consider what we will do when Antarctica comes to our door. World leaders, if we lose the light of Antarctica, we lose the world. I have a vision. I see a world where we are successful in halting temperature increase at 1.5 degrees and living in harmony with nature. Here in this world, women and indigenous people take their rightful seat at the table to take action, and youth are taken seriously. In this vision, I see equitable and sustainable cities thriving. In this world, there is social equality and social justice, cooperation and abundance. There is peace. I see healthy ecosystem and forests providing food, clean water, and supporting livelihood and economies for communities in Cameroon, in Africa, and in the entire world. But this dream is at risk. Climate change requires urgent systemic solutions and transitions. Climate impact are not just about the environment, but also about billions of displaced people, gender inequalities, social injustice, and human conflict impacting all nations worldwide. Women, underrepresented groups, and children, small island states, and the global south are the most at risk. World leaders, please, this is the most challenging time in human history, and it is one in which we must succeed together in safeguarding the planet. Join me in this vision, share it with your people, and make it a reality. I call on you all to secure our future by investing in grassroots women and youth initiatives for immediate action. The time has come to mobilize resources on the front line of this global crisis. I therefore request for the parties present at this COP28 take action in 4 key points. The first is to be world leaders we so urgently need, with one voice for a shared future. 2, urgently phase out fossil fuel and accelerate the shift to sustainable and gender-responsive nature-based technologies. 3, deliver prompt climate finance for local communities, women and girls from the global south. They know what needs to be done to solve their problems, and they have been historically under-supported and underfunded. The 4th one is secure women rights and land tenure rights for rural women and girls to enable their leadership. Climate finance must not leave indigenous and local community women and girls behind. Work with us, together we can succeed. Thank you very much for the opportunity. Please share that. Thank you.
Thank you. I know that's a hard act to follow, but more questions, please.
Hi, I'm with Radio Free Asia. I'm based in Bangkok. I wanted to ask a bit more about the impact, glacier melting impact on Asia. Specifically, has there been any studies done on Tibetan Plateau?
There are studies, and they're sort of the one important thing is, for instance, that the size of the lakes has increased. There's a recent study, and there's a number of studies on the impact on runoff, which are all along the lines what I was talking about. So some regions getting more water, annual runoff, others less, depending where on this curve they are. And also that the seasonal variability really matters, that especially in the dry season, that regions experience also already a decline in glacier runoff.
Please, Martin.
Yeah, hi there. Excuse me, Martin Seegert, University of Exeter, and a polar scientist. Those were great talks, by the way, and wonderful intervention just now as well. Thank you for all of that. I'm still learning, right, even after 30 years of doing this sort of stuff. What I'd like to ask the panel is, there was several mention to sea level projections, and from the IPCC, and then discussions about what happens after net zero, and all fine. Most of those discussions are captured within probabilities of what might happen, but not possibilities of what might happen. And I think we have created a narrative of comfort by thinking about probability, when actually the really worrying thing is what might happen outside of that 66% probability. That is a 1 in 3 chance of being worse than some of these things that we're projecting. And it goes for sea level change, but it also goes for what happens after net zero. And I wonder, just to appreciate the panel's comments on their perception of what might be possible, worst case scenario, rather than probable. Thank you.
Well, I will try to to answer the question. So I truly believe that, for example, in the IPCC projection, there is this dotted line that refers to structure, expert judgments, and other physics that we are currently investigating. That is outside of the range of, let's say, the scenarios of projections. I'm more keen to think that this structure expert judgment is something that really is a possibility to happen, because as a paleoclimate person, I saw definitely that this happened. So I know this is definitely possible, and it's not only a probability. So to me, I mean, even if right now we are still investigating the physics, and we do not understand the extent of all the processes going on, I truly believe that this dotted line is not only about parameterization in a model, but reflects definitely what is possible and already happened. So yeah.
And we just chose to, because we can do this fairly quickly, to bring up a map. If someone's wondering why someone from Cameroon should care about what happens with Antarctica, this is why. This is 3 meters, which could occur as early as the beginning of next century. But then here we have 6 meters. And there's not a whole lot left. And that's why it's so important that these boundaries be respected. Yeah, possibilities versus probabilities. Yeah, in a way, we won't be able to say until it actually happens. But one reason, actually, I decided to start ICCI was due to conversations I was having with scientists offline about what they really thought was going to happen. And I will say uniformly, and I'm going back now to say 2007, 2008, what they thought was going to happen, that they were almost afraid to say publicly, has been exceeded. in nearly all cases. In other words, what they thought was would really happen as a worst case scenario, we've exceeded that already with observations, say on how much melt could come off of Greenland. There was a thought in the early 2000s to mid 2000s really that Greenland, it's a lot of ice, right? If it starts melting, it's going to take a really long time. Well, now the median for if today's emissions continue just from Greenland has gone up in recent papers to about 3.7 meters contribution by 2300, and that's just from Greenland. And that Greenland melts linearly, right? It's a big hunk of ice, and it takes a while to melt. You melt surface, you melt at the edges. Unlike Antarctica, what Flo showed, where you could have a collapse that, you know, sudden means a couple of hundred years, but still, once that collapse starts, it's very, very hard to stop. But I have to say, as someone working in this, when I saw that 3.7, that was actually an increase from the previous median, which was 3.2, which is bad enough. But I hadn't even realized that Greenland could contribute that much that quickly.
Just comment, and that's a very good question, actually. And as you're kind of alluding to, the IPCC formal assessment process has struggled to deal with the question that you're raising. If you think back to the fourth assessment report, you'll find that there was virtually nothing said about the risk of ice sheet disintegration. That led to a bit of an outburst in the literature about that, and that was partly because, well, on the one hand, some ice modelers said this, on the other hand, some ice modelers said that, and observationals said this, and the chairs, in their wisdom, decided that nothing would be said. Now, fast forward to the sixth assessment report, and I think the point that was made, France, is absolutely correct. Working Group 1 has a really spectacularly important figure in it on ice sheets. You've got, of course, the medians, the probability ranges of the modelled assessments, but then you've got this very alarming line that goes up to 2,300 and many metres of sea level rise, which is a codification of the expert community's feeling about what could happen, right? And I think that is one example, and Earth system feedbacks and responses to emission reductions and warming need to be the next evolution of the IPCC, because, you know, we have no real guarantee that we will not have large carbon cycle feedbacks of one form or another that will make it a lot harder to limit warming to 1.5 degrees, and that will require much larger negative emissions, you know. And I think if you scratch the surface of some of the carbon cycle people I've known for 20 odd years, 25 years around here the last week, that's what they will tell you. It's a mess. And so I think the IPCC assessment process needs to try and embed that, right? And really bring that through to policymakers. It's very hard, you know, with a bunch of scientists all sitting together trying to reach a consensus about their assessment in their area. You will gradually move towards the median. And so having a more formalised assessment process that allows an expression, as was done in Working Group 1, this last assessment of the possibility, will really convey the risk to policymakers in a better way than we're doing at present, I think.
Thank you. And I'll say one of the reasons we're comfortable, at least organizationally, showing maps like this is because since the sixth assessment came out, that dotted line was based on 2 studies, one an expert judgment, but the other a modeling study, a projection. There have been several studies that have come out, and unfortunately they all point to the dotted line. The second thing is that observations of the way, especially the West Antarctic ice sheet, but parts of East Antarctica are actually behaving today in terms of losing ice, are tracking also with that dotted line. And so that's why it's important to consider this and to consider the risks we're taking by continued warming, because we're only at 1.2 at this point in time. We have time for maybe 2 more questions, about 4 minutes.
Thank you for a wonderful panel and also for the follow-up. I'm Letizia Tedesco. I'm based out of the Finnish Environment Institute. I'm a polar and marine scientist. So I have a question for all of you I want to answer. There's been several events at this COP about climate intervention, and as the only way to stick to 1.5 degree, because anything else is feasible. And I'm wondering, when it comes to the cryosphere, to solar radiation management, or to this curtain at the seabed, to prevent the melting of ice sheets, if you have an opinion, you want to comment on that. Thank you.
Thank you. Perhaps I'll start, if that's okay. Yeah, I keep seeing some of these events. There are two big events on this also this afternoon, so please, we need a lot of scientists to attend them. I'm extremely concerned by geoengineering, especially solar radiation management. I think we need to be fully aware that the argument I keep hearing is, oh, it's going to buy us more time. The reality is it might buy more time for the fossil fuel industry. When we send particles, aerosols into the stratosphere, the consequences can be absolutely major, such as acid rains. It could disturb the water cycle. It could disturb where the monsoon will fall, and it's billions of people who will be affected. And we really need to look at the ethics behind geoengineering. Who is funding it? Who has a voice? You know, who's going to make the decision? We don't have a governance system at the moment. But also, and that was raised by Valérie Masson-Delmotte as the Polar Summit in Paris, who's going to pay for the damages, the repairs, if something goes wrong? And we already cannot raise enough money here for loss and damage connected to fossil fuels. What about geoengineering? So let's not underestimate the negative consequences of geoengineering. It's extremely concerning, yeah.
And I'm just going to list three things. Polar ocean acidification, right? If CO2 in the atmosphere is going up, then we're going to see spreading acidification and lack of shelled life really to be able to survive in both polar oceans. That's number one. Number two, we have a fairly good idea what would happen because of past volcanic eruptions. This is cited in terms of decreasing temperatures, but let's look at massive crop failure across the entire northern hemisphere and disturbance of the Indian monsoon as a consequence of that. And also what is known as I forget the technical term for it, but temperature rebound. And it's important, I think, for the community to think about it in this way also, that keeping heat out is not the same as keeping heat in, which is what CO2 does. The Earth system responds differently. And so it's not a matter of global mean temperature, it's about just a completely different Earth system. Those three things alone are why I'm sure there must be cryosphere scientists somewhere who maybe support it, but I don't know a single one. And it upsets most cryosphere scientists that I know that their science is being used to promote this because they disagree with it. I don't know if either of you wish to comment.
Well, what I wanted to say in this line is that we don't know enough to really have a real opinion on the matter. And the thing is, we are not really informed. It comes like secret studies, and so we don't really have a real scientific approach to that. And so, yeah. So, okay.
Okay. Yeah. All right. We are out of time. Thank you very much for coming here, and we really appreciate your participation, and feel free to ask questions of us outside, but we'll of course need to vacate the room for the next event so they can get started. So thank you very much.